All right, guys, here we go. We have part two of radians, arc length, and angular speed. I know you're excited. We talked about radians in the last one. I'm not feeling very well. Sorry. So, if I don't make the same wonderful jokes that you've come used to, or if I'm not as excited, I really apologize for that. Both my kids have the flu, and now, oh no, I'm not getting it. Nope, I'm not gonna get it. So, we all got the shot, by the way. I know that's what you're thinking. That's what I would be thinking too. Remember we defined a radian to be before. So a radian is this new way to measure our angles. And we defined a radian if we had, oh guys, I'm gonna have to draw the circle. It's all right. So if I had a circle of radius 1, okay, so circle of radius 1. Oh wow, that's weird, it made it. Huh. Okay, good enough. Good enough. Remember, so what we define a radian to be is if I could measure exactly along the circle here, if I could measure exactly one distance. So my arc length, right, is the length around that circle. If I could let that be 1, then whatever that angle is that measures that 1 across, that's going to be what 1 radian is. But we want to think about radians. We don't have to be in a circle of just radius 1. So that's what we're going to look at today, is like how we can actually, using radian measure, define arc length a little bit differently, and we don't have to have radius 1. So let's keep the purple circle. We'll let that be radius 1, and then let's create another circle of radius r. Oh no, 2 circles, guys. I'm sorry. This one maybe isn't quite. See, I say it's not going to be bad, and I shouldn't say that. Okay, so a couple things here. So let's just we know that let's get an angle first of all, okay? And so I'm going to look at my angle. Here's the initial side, and it doesn't really matter where I put this angle. We say in mathematics it's called without loss of generality. I'll just put it in the second quadrant, but this angle could go in any of the quadrants, okay? So here's a couple things that we know. We know that this distance here from the center to the purple line is 1, because this is still going to be my unit circle. And then I've defined this distance right here then, right, must be, let's just call this r for some radius. Okay, so the gray is going to be a circle of radius r, so it doesn't have to be 1 now. And then the purple is going to be a circle of radius 1. So that's going to be our unit circle. Okay. I really hope whatever I'm teaching you today is true. I just am not sure, because I'm not well, but that's all right. We'll be okay. All right. If I tell myself that enough, then I'm gonna it has to be true. So a couple other things here. We're gonna look at some distances. So what I'm going to call, let's talk about arc length. So this arc length right here, so see this purple right here that I'm kind of making a little bit bolder? Let's call that arc length right there, let's call that S sub 1 for the arc length of that kind of piece. There's some fancy words you can use, it's a center angle that subtends, I believe it is, an arc length or something like that. I don't remember my geometry. I don't teach geometry, and when you haven't had it in a long time, you kind of forget it. So I'm gonna just say that this arc length right here is, we'll say its distance is S1, and then this distance that the yellow angle subtends, that sounds really good. I'm gonna call it subtends. We'll just say that that length is S. So again, that S represents the length, right, or the distance you would travel along the circle from the initial side of my angle theta, the yellow angle, to the terminal side. Okay, so a couple things to observe here. If we have something like this, again, we know that the purple circle is of radius 1. We actually can do a proportion, and these are going to be proportional to each other. So what I mean by proportion is the radius of the unit circle and the non-unit circle, and then the actual length, right, of that arc length, they're going to be proportional to each other because they have that same central angle. which is that yellow angle. So basically, if I take proportions, right, if I take S is to S1, so I'm taking the arc length of my bigger circle and I'm relating it to the arc length of my unit circle, then that's going to be the same as the radius. So what is the radius of my big circle? That is, or the proportion of the radii. That's r, and then what is the radius of my inner circle, the s sub 1? We know what that is. That's going to be 1, all right? So I'm just going to mess with this a little bit. So I'm going to flip both sides of it because I can. So I'm going to so I'm going to flip both sides of this. So I'm going to get s sub 1 all over s because I know none of this is 0. And this is 1 over r. And then just for fun, I'm going to solve for s sub 1. So s sub 1 equals r over 1. Okay, and then what we know about s sub 1 though, remember what a radian was. A radian, 1 radian, right, was traveling 1, that would be the angle I would need to travel exactly 1 distance on the circle. So if I travel s sub 1 distances on the circle, then that just means that my radian then is that measure. So this s sub 1 right here is going to be the radian measure of that angle theta, right? That yellow angle, this angle theta right here. This right here corresponds to the radian measure, not the degree measure, but the radian measure of that angle. And that's exactly what we talked about with what it means to have a radian measure. Measure? That's how my mom says measure. She's from South Dakota. Measure. So thus, what is this? There is a point to this, I promise. Oh, whoops, I forgot to, oh, Sarah, I'm sorry. You guys saw that. You saw that, I'm sure. I'm sure you're yelling at the computer. That's my fault. I apologize. S sub 1 then, if I multiply both sides here by s, this is what I meant to do, is s over r. So the important thing that we can see here is now we have a relationship between, okay, we have a relationship between the radian measure of an angle, the arc length of that kind of chunk of the circle that the angle subtends, and the radius of my circle. And I don't have to have a radius 1 anymore. Okay, so let's write this down. And I'm sorry, if I really do apologize if I'm kind of all over the place. So another way to talk about radian measure. Let's talk about let's define this, put this down a little more nicely when we have an instance where we don't have the unit circle. Okay, so the radian measure, which we used to define in the unit circle, was just that distance, right, that something would travel through that angle. But now the radian measure of theta is the ratio of the arc length arc length the angle subtends. That is the right word. I feel very smart saying that. Look, my pen's a little lagging here. I'm gonna have to probably get new batteries for it. Subtends, it's the ratio of the arc length of the angle subtends and the radius. Okay, so another way to say that is theta equals the ratio of the arc length and the radius. Another way to think of that, if I put this guy, let's say in the first quadrant, right, but this is r now, and this is theta, and this distance here is s. Okay, so let's do an example. So we can use this to find theta, we can use this to find arc length, we could use it to find my radius. Let's do arc length first. So find the arc length of the segment of the circle, right? When we say arc length, maybe that kind of, well, it doesn't always imply it's a circle, but of the segment subtended by the angle 4 pi over 3 in a circle of radius 4 centimeters. So, you're going to need to memorize this formula that the theta equals S over R, but that shouldn't be too hard, hopefully, to do. And we just kind of plug in. So once you have this, we know that theta then is S over R. And so what are we given and what do we want to know? So we're given, right, that my theta is 4 pi over 3. We're given that my radius is 4. And so now we should be able to solve for that S pretty easily. Well, it's easy to say that, right? But sometimes the devil is in the details when you... So what is this going to equal? This is going to equal S over 4. And if we want to look at our units, which we really should, this is S over 4 centimeters. Just multiply both sides by 4. And what do we get this to be? We get this to be, what, 16 pi over 3? And remember, radians don't have any units to them, so we'll just keep those centimeters. So we get 16 pi over 3 centimeters. Again, is that really useful, though? I don't know. If you go to Home Depot and ask for 16 pi over 3 of something, they're going to look at you like you're crazy. But what would S be? This would be about 16 point, if I rounded, 76 centimeters. Okay, that again, what would that give you? That'd give you that distance of that segment of the circle that is subtended by that angle. All right, let's do another one. The one thing to always remember is that theta has to be in radian measure. So clearly I'm going to do one that's not. Oh wow, what did I do there? All right, so another example. Okay, in a circle with a 10-foot diameter, actually, I'm gonna do, I want to do one a little bit differently here. So let's say given, okay, so let's say given an angle, whoa, wow, sorry. Given an angle of 45 degrees that subtends a segment. I don't know if I'm using subtends in the right format, but subtends a segment, let's say 200 inches. Determine the length of the radius. Okay, so again, if you know, some books will go through and they'll like take this theta equals S over R and they'll give you like 3 different equations to memorize. One where S is by itself, one where R is by itself, and one where theta is by itself. Don't do that. Just memorize that theta is S over R and then see what you're given and see what you want to know and then solve from there. So what do we know? We know that theta is 45 degrees, but remember people, this whole thing here is a definition of radian measure. So theta can't be 45 degrees if I'm going to use this formula. This formula is in radian measure by definition. So remember 45 degrees. So remember how we would, if you don't remember it, that's one that you should figure out. You know that in radian measure right away. But if you don't remember that, remember to multiply by pi over 180. 45 goes into 180 4 times. So 45 degrees is the same as pi over 4. So I'm going to plug in pi over 4 for theta. What else do I know? I know that subtends a segment of 200 inches. So what else do I know? I know S. So that's going to be 200. And then this is all going to be over R. Okay. Now, if you notice, the thing that I want to solve for is in the denominator. So what I like to do, you guys can cross multiply if you want. I really hate cross multiplication. I find my students don't quite know when to use it and when not to. You can use cross multiplication when you have 2 fractions equal to each other, but just in calculus the other day, I had some students want to cross multiply when we didn't even have an equal sign and we weren't even solving an equation. So please be careful with the cross multiplying. So I'm actually just going to flip both sides. I like to flip that so that my r is on top. Now that my r is on top, I can multiply both sides by 200. And remember, these are 200 inches, right? So what is the radius of my circle? This is pretty big, 800 inches over pi. That's going to be the radius of my circle, or if I figure that out, that's going to be about 254 inches. 254.65 inches, okay? So I think it's a pretty simple formula to use. It's just a matter of remembering, what the formula is, and then remember that theta, it has to be in radians. You may not use degrees for that because that's what we learned. All right, last two topics, you guys, and then we will call it good. I need to call it good. I have to go teach a pretty major lecture in calculus, and we'll see what I teach them. It'll be quite interesting, I'm sure. All right, so I'm going to make a couple definitions here. We're going to do two last kind of things that are kind of interesting when we're looking at this stuff. So the first thing I want to talk about is this idea of linear and angular speed. So I'm actually just going to kind of write down how we find them, and then I'll talk about why maybe I hope you think this makes sense. So speed, right? We know distance is rate times time. We've all heard that before. And if you solve that rate that they have in that distance equals rate times time, right? That rate is basically your speed. So this R right now is not standing for radius, it's standing for rate. And if you solve for that, I mean, if you think about this, speed kind of makes sense. Speed is just basically the distance you travel over the time it takes you to get there. If I'm driving to Rollins and it's 100 miles from Rock Springs and it takes me an hour, I'm driving too fast because I've gone 100 miles in 1 hour, and I should have probably got picked up by the cops because I'm going 100 miles per hour, right? That's my speed. So with something like that I just was describing, that's what we call our linear speed. So in the case of, let's say we're on a circle, right? And we want to know how fast we are traveling around that circle. So like if you're on a Ferris wheel or something like that, and you wanted to know the speed at which you're going around that Ferris wheel, there are a couple ways that we can actually describe travel along a circle. So I can look at this speed, again, is distance over time. So I could look at, guys, that was a pretty good circle. Maybe I'm overthinking it. I could look at how far have I gone in a certain amount of time, or how long would it take me to travel this distance right here, right, in a certain amount of time. Again, what have we been calling these distances? Those are arc length. So we're going to define our linear speed, and we're going to call this v for velocity, right? So our linear speed, okay, is going to be the arc length, or the distance we've traveled on the circle, over the time it took. Again, remember, this S right here is arc length. So when we say speed, don't confuse that. I'm going to give you these formulas for the linear and angular speed on the test. I will not be giving you the theta equals S over R, so you need to know that. But I will give you the linear and angular speed. I won't define what the variables mean, though, so make sure you understand what those variables are. So my linear speed is just going to be the distance along my arc length, the distance along the circle, divided by my time. Well, there's another way that we can think of speed, though, if we're traveling along a circle. I could also think of speed as being, well, what is the angle that I've gone through, right? And how long did it take me? So for example, if I want to know how long it took me to go from 0 degrees, right, to whatever, well, I should be in radians. Let's be in radians, 0 radians. To 3 pi over 4, that could be a speed as well. And that is what we call our angular speed. How long did it take me to go from an angle of 0 to an angle of 3 pi over 4? We're going to give that a little bit of a different, I don't want to use V again, because V we usually reserve for like a distance, not in angles, but just like a displacement kind of along a curve. So V is S over T. So I'm going to use a different one. You're going to say it's W, but it's actually omega. So I put a little kind of squiggly thing on it. It's a Greek letter. And again, this is just, what have I the distance I've traveled, but in terms of angle divided by time. Okay, so two things for angular speed, and then we have a way to actually relate these two together. Okay, so these two are important to know. I'll give you these, but you don't need to know how to use them. And then I want to show you how they're related. So recall, because it just happened like 10 minutes ago, theta equals S over R, right? So if I solved this for S, so multiply both sides by R, that means S is going to be R times theta. But look at what I know here. I know velocity is S over T. So I'm gonna take, oh, sorry about that. I think that I just messed up my, 1 second. Okay, sorry about that. So what I'm going to do, I want to see basically how the linear and angular speed are related. So I'm going to take this S and I'm going to divide it by T. But if I do it to one side, you best be doing it to the other side, right? And so what is S divided by T? Well, I have just defined that to be my linear speed, which is my velocity. And then let's look at over here. I can actually rewrite this as R times, and let's just look at kind of breaking that theta over T out. Why would I do that? Because my theta over T is my angular speed. So this gives me a relationship between linear speed and angular speed. So linear speed in terms of angular speed, we're going to do some examples, I promise, is given by my angular speed is just my radius times omega, okay, times my angular speed. That's it. So those are the important ones that we're going to use. We're going to use, this is my linear speed, how fast am I moving along the outside of the circle. This is my angular speed, what is the angle that I went through in a certain amount of time, or what, yeah, that's my speed. And then my linear speed is equal to my radius times my angular speed. Let's do some examples. Did I just get rid of the wrong one? No, that one is good. Okay. So 2 examples and then we'll call it good. Okay, a wheel with a 30 centimeter radius is rotating at a rate of 3 radians per second. Okay, what is the linear speed of a point on its rim? And let's do meters per second. Let's just try it. Make sure you look at your units. Oh, meters per minute, not second. Oh, this is going to be a good time. Let's first find it in centimeters per second, and then we'll figure out meters per minute. Okay, so a wheel with a 30 centimeter radius is rotating at a rate of 3 radians per second. What is the linear speed of a point on its rim in meters per second? So what are some things I know? I know that R, so let's start writing down some stuff we know. I know that R is 30 centimeters. And let's try and figure out if we can determine, well, we can, but what this means right here. So it's rotating at a rate of 3 radians per second. So is that angular speed or is that linear speed? Well, angular speed would be something like 30 centimeters per second, or meters per second, or feet per second, or inches per second. Radians here, right, is a measure of an angle. So what this must be then, this 3 radians per second, this must be omega. It's 3 radians per second. And remember, 3 radians, well, this is 3.14 radians, right? So it's gone basically almost that far, right, in 1 second. That's what that's saying. And now, what is the linear speed of a point on the rim in meters per minute? So I have a point on the rim of this wheel, right? Here's my wheel. I know my wheel is radius 30 centimeters, and I know that my linear speed is equal to my radius times, right, my angular speed. So this should be pretty simple, other than we're going to have to do a little bit of a unit conversion. So my linear speed, I'll have 30 centimeters. Now radians actually don't have any units, so I'm just going to make that a 3/1 second. So look at what I know. I know that my linear speed is we are rotating 90 centimeters per second. Okay, we're doing 3 radians per second. 30 centimeters is my radius. So my total linear speed is 90 centimeters per second. Now what do we want though? We want meters per second. And I believe that there are 100 centimeters in a meter. So I'm going to multiply 1 meter is the same as 100 centimeters. I want the centimeters on the bottom so that those cancel out. And then I want per minute. I know that there are 60 seconds in 1 minute. So the seconds are going to cancel out, right? And look at what I'm going to be left with, meters per minute, which is exactly what I want. I can start canceling some zeros. So it looks like my answer is 54 meters per minute. Okay? Not too bad, right? That's not too bad. Not too bad. Maybe not too good, but not too bad. All right, let's look at one more example, and then I think I got to be done. I got to go. Let's see if I can make up something in calculus today. All right, last one. Okay, the Earth has, and I love examples like this with any of the planets, I just think it's interesting, has a 4,000 mile radius from its center, right? What is the linear speed? So this one we're going to have to think about for a minute. Of a point on its equator. In miles per hour. And it almost seems like I haven't given you enough information, but I promise I have. Well, I have, as long as we think a little bit about it. So the Earth has a 4,000 mile radius. What is the linear speed of a point on its equator in miles per hour? So linear speed, again, a couple ways that I could think of linear speed. I could think of the distance it's traveled over time, which I don't think that's going to help me right now. I think what's going to help me the most is that if I can figure out my angular speed of a point on the equator, that's what is going to help me out. So think of a point on the equator. What is the angular speed? Or is there any way that we can determine a radian, measure an angle that I go through over a certain amount of time? Because remember, angular speed is theta over t. Well, there sure is. What do we know about Earth? We know that it makes one full revolution, right? In what? 24 hours. That's the definition of a day. And what in one revolution, what do I know? How many radians have I gone through in one revolution? Well, I've gone 360 degrees, which is the same thing as 2 pi. So that's going to be in 24 hours. That's going to be what I'm going to use for my angular speed, and then I'm raring to go. And I might as well simplify this while I'm here. That means we do pi in 12 hours, which makes sense. I've gone halfway around in 12 hours, right? Just cancel the 2. And so here we go. Linear speed then. What is my radius? 4,000 miles, right? And I'm going to be in miles per hour right away, times pi over 12 hours. Now I'm excited to see what this is. So what is my linear speed, right? That's how fast someone right on the equator is going. Times pi divided by 12. Nice. We're going about 1,047.2 miles per hour. And it doesn't even feel like it. All right, you guys, I gotta stop. I'm so sorry. I'm sorry if I wasn't very coherent or anything. Please feel free to email me any questions if you have any over the homework or over this lecture or life in general. I'd be happy to try and answer them. Okay, you guys, have a great day.